This is a wastewater and sewage treatment plant, the kind most people think about. This is a wastewater and sewage treatment plant too. Maybe not the kind you think of when you think of wastewater treatment, but just as important and much more common than most people realize. In fact, as many as 40 million households in the U.S. currently use on-site treatment to meet their wastewater and effluent disposal requirements, and the numbers are growing. To satisfy this growing demand, the Sump and Sewage Pump Manufacturers Association, an organization representing more than 85% of North America's sump, effluent, and sewage pump manufacturers, is working closely with on-site contractors, engineers, government regulators, research academics, and trainers in developing ways to make it easier to successfully match the equipment to the job. This video, along with the accompanying work materials, deals with the sizing and selection of an effluent pump for your particular application. Pumps are used in a number of widely diverse applications. In this presentation, we will be dealing primarily with two of the more common systems: enhanced flow septic tank pumping and low pressure pipe distribution. However, the principles governing pipe size, pump selection, and control settings can be applied to other applications as well. As a first step, perhaps we should examine the anatomy of a typical septic system. The basic function of a wastewater treatment system is to receive wastewater, typically solids and fluids, store it temporarily, then move the relatively clear effluent into a pump chamber. There are numerous variations, of course, depending on the application and conditions, but the system illustrated here, an enhanced flow step system, will serve to demonstrate the basic elements of most systems. In this typical residential system, liquid waste discharge from all household sources flows into a central gathering point, a septic tank. There, after settling or other treatment, the effluent is collected in a pumping chamber and pumped to a lateral field via a pressurized manifold or distribution box. In applications where soil conditions are unfavorable, water tables are high, or other limiting factors exist, a low-pressure pipe system may be the preferred approach, or in some cases, the only practical approach. Even in good soil, an LPP system may be the best option to ensure life of the drain field. In these systems, a predetermined volume of effluent is evenly distributed at low pressure throughout an absorption field. The distribution network consists of small diameter pipe with uniformly spaced small diameter holes. In either system, a pump is required for the lifting and transfer of the calculated volume of effluent at a rate to meet the demands of the system, a pump of the correct type and performance characteristics. During this presentation, we'll be using several terms common to the industry. You're probably already familiar with most of them, but it might be well to review the terminology we'll be using. Effluent is the pre-treated liquid waste discharge from an on-site sewage treatment system. Effluent pump is a pump designed for transfer of effluent. STEP, septic tank effluent pump system, is a conventional septic tank system in which effluent is pumped to a distribution manifold or a distribution box for conventional distribution, or in some cases, a sewer line. Enhanced flow system, a step system in which a pre-calculated volume of effluent is pumped to a distribution box or pressurized manifold to utilize the entire conventional distribution field. Low-pressure pipe system, a system in which effluent is evenly distributed at low pressure via small diameter pipe with evenly spaced small diameter drilled holes. The conditions which dictate this type of system will be discussed later. Pump capacity, rate of flow stated in gallons per minute. Minimum velocity, the rate of flow necessary to carry solids, generally accepted to be 2 feet per second. Static head, the actual vertical distance measured from the minimum water level in the pump chamber to the point of discharge. Friction head, the additional head created in the discharge system by resistance to flow within the pipes and other system components. System operating head, pressure required to operate the system. For purposes of calculation, in an enhanced flow step system to a distribution box, the operating head is always 0. LPP systems typically have an operating head of 2 to 8 feet specified by the designer. Total dynamic head, combined total of static, friction, and operating head. The total pressure required to lift the effluent from the receiver basin and effectively push it out through the pipes into the absorption field. Before proceeding to the calculations required in sizing and selecting a pump, it might be well to review the basics of submersible wastewater pumps, what they are and how they work. The pump itself consists of a rotating impeller working inside a stationary housing. An electric motor drives the impeller, which transfers motion to the liquid surrounding it. The liquid inside the casing is then forced by centrifugal force out through the pump discharge. Unlike the operation of other centrifugal pumps, solids must be able to pass through a submersible sewage or effluent pump. This requires a special non-clog impeller design and adequate clearance between the impeller and the wall of the casing, reducing the potential for solids becoming lodged or clogged between the impeller and casing. Impeller designs generally fall into 4 basic types: open, semi-open, enclosed, and vortex. The open impeller design has no backplate, and the vanes extend from the center of the impeller outward. Pumps incorporating an open impeller design are used chiefly in low to medium pressure, high capacity pumps capable of handling screened or unscreened solids. A semi-open impeller has a solid backplate to which the vanes are attached. Enclosed impeller designs incorporate a solid plate on both sides of the vanes. In the vortex impeller, vanes with shortened height are used so that the liquid and solids pass between the edges of the vanes and volute by whirlpool action. How do we go about matching a pump to the job? Let's find out. First, thoroughly familiarize yourself with local codes governing wastewater treatment systems. These can vary greatly from place to place, depending on such factors as soil conditions, proximity and depth of aquifers, and other environmental considerations. Now, for actual selection and sizing of the pump. 2 primary factors will enter into our pump selection process. 1, the flow rate or pump capacity required to meet the demand of the system. And 2, total dynamic head. The demand of the system is determined by local codes and/or the system designer. Minimum pump capacity is that flow rate necessary to transport solids generally accepted to be equal to a velocity of 2 feet per second. For most applications, the minimum flow requirements are sufficient. Worksheet number 1 illustrates the relationship between the diameter of pipe and minimum acceptable flow rate. For example, in a 1.5-inch pipe, we'll need a pump capable of pumping at least 12 gallons a minute. 2-inch pipe, 21 gallons a minute, and so forth. As you remember from our definitions of terminology, total dynamic head, or TDH, expressed in feet, is a total of static head plus friction head plus operating head, if any. TDH is the force required to transfer effluent from the lowest point in the system to its destination. Now, let's work through the steps required in matching a pump for a hypothetical system. Since total dynamic head is the sum of static head, friction head, and operating head, we'll first calculate these values separately, then add them. Static head is the actual vertical distance in feet measured from the minimum water level in the pump chamber, normally the off point of the pump, to the point of discharge into the manifold or distribution box. In the illustration here, 6 feet. A word of caution: the point of discharge may not be the highest point in the piping system. The pump selected must have a head greater than the highest point in the pipe system. For purposes of this problem, our static head of 6 feet should be entered into your worksheet for calculating total dynamic head. Friction head is the resistance to flow within the discharge system. The friction within the straight pipe plus the resistance to flow created by the fittings, elbows, valves, and other system components. In calculating friction head, these components must be converted to an equivalent length of straight pipe. To calculate friction head, first measure the length of discharge pipe from the discharge opening of the pump to the point of discharge into the manifold or distribution box. Since friction loss in the pipe is a factor of pipe size versus flow rate, for example, the smaller the pipe size or the greater the flow rate, the greater the friction loss. Refer to Table B in your work materials for the friction loss per 100 feet of pipe. To determine the equivalent length of discharge pipe represented by the various fittings, valves, or other components, refer to Table A in your work materials. The total of these values plus the actual measured length of pipe equals the total equivalent length of pipe. The total equivalent length is divided by 100 and then multiplied by the friction loss factor from Table B. And remember, static head plus friction head plus operating head yields total dynamic head. In our hypothetical step system, we've determined that we have a static head of 6 feet, the vertical distance from the minimum water level in the pump chamber to the point of discharge into the manifold or distribution box. We enter this number as the static head on the worksheet. As our system is laid out, we have 170 feet of 1.5-inch pipe. We also have one 90-degree elbow, 2 45s, a check valve, and a union. Referring to the table in our work materials, we find an equivalent of 8 feet of pipe for the 90-degree elbow, 3 feet for each of the 45s, 13 feet for the check valve, and 1 foot for the union, for a total of 28 feet, the equivalent of 28 feet of straight pipe represented by the fittings. When added to the 170 feet of discharge pipe, we have a total of 198 feet, or, rounding up to the nearest 10 feet, 200 feet for purposes of our calculation. Referring this time to Table B for friction loss per 100 feet of 1.5-inch pipe with a flow rate of 12 gallons per minute, we find a friction loss of 1.1 feet per 100 feet of pipe. And since we are calculating on the basis of two 100-foot lengths, we multiply this by 1.1, the friction loss per 100 feet from the table, and get a total of 2.2 feet of friction head. Now, adding the static head of 6 feet to the 2.2 feet friction head and 0 for the operating head, because this is an enhanced flow step system, we have 8.2 feet of total dynamic head. Once we have the total dynamic head and the gallons per minute required, we can size the pump. In this example, we've determined that we need a pump with a capacity of 12 gallons per minute at 8.2 feet total dynamic head. Now, let's go through the steps in setting pump requirements for the other type of system we'll be treating in this presentation, a low-pressure pipe system. Once the parameters have been determined, actual selection of the pump is essentially the same as in a step system. In LPP systems, effluent at low pressure is delivered evenly throughout the dosing field. The distribution network consists of small diameter pipe with evenly spaced small diameter holes. Although we will be discussing pump selection for LPP systems, the same principles also apply to sand filters, peat systems, and mound systems. The first step is determining pump capacity, the rate of flow expressed in gallons per minute, required to make the system function properly. We do this by examining the proposed distribution network, including length and diameter of pipe, number and type of fittings, hole sizes, number of holes, and operating head. In this system, we have specified 1.5-inch pipe, but keep in mind local codes may dictate pipe size. Operating head is the pressure which must be maintained in a lateral, expressed in feet of head, usually measured by an open standpipe temporarily placed at the end of a lateral and adjusted by valves in each lateral or according to your local code. Flow, expressed as gallons per minute, can be calculated by multiplying the number of holes by the flow rate corresponding to hole size and operating head. Using worksheet number 2 and the tables included in your work materials, let's work through an example. In this system, we have 25 3/16 holes, an operating head of 3 feet, and laterals all at the same grade. Referring to Table C for flow rate as a function of operating head and hole diameter, included in your work materials, we can read across from the 3 feet of operating head to the 3/16 hole diameter column and find 0.72 gallons per minute. Multiplying 25 holes by this 0.72 gallons per minute, we find we'll need a pump capable of maintaining a flow rate of 18 gallons per minute at the total dynamic head, which we are now ready to calculate. Calculating total dynamic head in an LPP system is much the same as in the step system. Remember, total dynamic head is the sum of the same 3 factors: static head, friction head, and operating head. As in a step system, static head is the vertical distance, measured from the minimum water level in the pump chamber to the highest point in the distribution field. A pump must be selected that has a head greater than the highest point in the system. In our hypothetical system here, we have a static head of 3 feet, and we'll enter this on our worksheet. Friction head, the additional head created in the system by resistance to flow within the pipe and components, is calculated as we did with the step system. First, measure the length of pipe from the discharge opening of the pump to the point of discharge into the manifold, following all contours and bends. In our system here, 150 feet. Next, we have to convert the fittings, valves, and other components to equivalent length of pipe. As before, we refer to Table A of equivalent lengths through fittings in your work materials. In this system, we have one 90-degree elbow, 2 45s, 1 check valve, and 1 union. Referring to Table A, we find that for 1.5-inch pipe, each 90 is the equivalent of 8 linear feet. 45s are equivalent to 3 feet, times 2 of them equals 6 feet of pipe. The check valve is the equivalent of 13 feet and the union 1 foot. Adding the equivalent pipe length of all these components, we have a total of 28 feet equivalent length of linear pipe for the fittings and valves. Add this to the 150 feet of actual measured pipe length, and we have a total of 178 feet, or again, rounding up to the nearest 10 feet, 180 feet of pipe for calculating friction loss. Since our table for friction loss is stated in 100-foot lengths of pipe, our 180 feet equals 1.8 100-foot lengths. From the table, we see that the friction factor in 1.5-inch pipe at a flow rate of 18 gallons per minute is 2.1 feet for each 100-foot length. When we multiply this 2.1 feet times 1.8, the number of 100-foot lengths, we get a total of approximately 3.8 feet of friction head. We enter this on our worksheet as friction head. As we learned earlier, friction head plus static head plus operating head is our total dynamic head. So we add 3.8 feet our friction head, 3 feet our static head, and 3 feet our design operating head. And we have 9.8, or, rounding up, 10 feet of total dynamic head. Our pump selection criteria for this low-pressure pipe system will be 18 gallons per minute at 10 feet total dynamic head. Now that we know what the pump must be able to do, how do we go about matching a pump to the job? The selection itself is simply a matter of finding a pump with the performance characteristics the job requires. Your pump manufacturer has performance curves available for each model and type. On the performance curve, plot the requirement of the application in terms of pumping rate required at the calculated total dynamic head, reading across the bottom scale of gallons per minute and up the left-hand scale to the feet of head. Remember, in our first example, the step system, we arrived at a figure of 12 gallons per minute at 8 feet of head. Plotting the point where the pumping rate and total head intersect, we find that the performance curves for either pump A or B satisfy that requirement. In our second example, our low-pressure pipe system, we required 18 gallons per minute at 10 feet of total dynamic head. In this case, only pump B will satisfy these requirements. One thing to keep in mind, depending on conditions, submersible wastewater pumps can vary as much as plus or minus 10% from manufacturers' published specs. So it's a good idea to build this into your sizing and selection. Before choosing a basin or pump chamber, it's imperative you consult local plumbing and/or building codes. Basins and pump chambers, most commonly of concrete, polyethylene, fiberglass, or coated steel, are required to be leak-proof and watertight. Other considerations include buoyancy prevention, structural loading, and other characteristics based on installation locale and local codes. Many local codes specify a minimum basin or pump chamber size, ranging all the way from 500 to 1,500 gallons for a residence. Some codes specify a basin or pump chamber capacity twice the expected daily flow, generally accepted as 150 gallons per bedroom per day. Controls to regulate the on-off pumping cycles are essential to every wastewater treatment system. These can range from a simple single switch to a complex panel, depending on specific application needs, and are generally divided into two broad categories: demand and timed pumping. With demand pumping cycles, wastewater flows into the receiver basin, and as the basin begins to fill, a switch floats up and turns on the pump. As the pump empties liquid from the basin, the fluid level falls until the switch turns the pump off. In a timed cycle control system, a timer is used to determine the amount and number of times a pump runs to pump a predetermined amount of effluent. A low-level cutout float will allow the timer to start the pump only if there is enough fluid in the tank to allow for satisfactory distribution throughout the absorption field. The amount of wastewater pumped per cycle is called drawdown, and when it is being distributed throughout an absorption field, it is also called a dose. Dose amounts are determined by the system designer and/or local codes. The volume to be pumped during each dose is expressed in gallons. For detailed information on dosing amounts, switch settings, and times for dosing applications, refer to the Sump and Sewage Pump Manufacturers Association publication, Recommended Guidelines for Sizing Effluent Pumps. Switches used to regulate these pumping functions are usually classified in one of two categories. Pump switches, capable of handling the higher amperage associated with direct control of a pump, are considered wide-angle, operating through an arc of 85 to 90 degrees, which allows the switch to control the level of effluent between upper and lower limits. Control switches are normally used for pilot duty with control panels and alarms. The amperage is usually limited to 5 amps and the operating angle is narrow, usually 3 to 30 degrees. An often overlooked but essential part of the control system is the junction box. The minimum acceptable NEMA rating is 4X, but again, check local codes. Since controls and switches will be working in a corrosive environment, all connections should be sealed with heat shrink, and cord connectors, if used, should also be rated to appropriate NEMA standards. For sealing conduit entrances, electrical sealing putty or pre-measured epoxy mixes are recommended. Options you might want to consider for your effluent control panel include switches for hand-off automatic control, high and low level alarms, pump run indicators, lockable latches, cycle counters, and elapsed time meters. Elapsed time meters and cycle counters are especially useful in diagnosing problems in the operation and maintenance of systems. A pump in a septic system should be inspected at least once a year, or more frequently if specified by the pump manufacturer or local codes. Systems with control options permit monitoring of the system. By monitoring the amp draw of the pump, length of pumping times, for example, and logging the results, a history of system performance is established and changes in performance can be evaluated. Now, let's review the primary steps in sizing and selection of a pump to fit the job. First, determine the pumping capacity required to maintain the minimum flow for proper functioning of the system. In a step system, refer to the table for flow rate in gallons per minute to maintain the 2 feet per second velocity in the size pipe you will be using. In an LPP system, refer to Table C, flow rate for various size holes, and multiply this times the number of holes. This will be the pump capacity required. Second, calculate the total dynamic head by adding static head, the actual vertical distance the wastewater will be lifted, to friction head, the resistance encountered by wastewater moving through the pipe. Be sure to include all friction losses, both in the pipe itself and various components such as fittings and valves, etc. Refer to the table in your work materials for equivalent length of each fitting. After adding the equivalent length to the actual length of the pipe itself, rounding up to the nearest 10 feet, refer to the table of friction loss per 100-foot length of pipe and multiply the factor from the table times the number of 100-foot lengths. This is the friction head expressed in feet. In a step system, operating head is always 0, so static head plus friction head will be your total dynamic head expressed in feet. In an LPP system, operating head must be added to obtain total dynamic head. On the manufacturer's performance curve for various pumps, plot the gallons per minute required versus total dynamic head in the system. This is your pump selection point and will dictate the size and type of pump required for your particular application. And keep in mind, the pump selection point must always fall below the manufacturer's performance curve. So you see, pump selection and sizing of a submersible effluent pump doesn't have to be difficult. A few pieces of basic information will determine the performance required, which can then be compared with pump manufacturers' performance curves and features available from all Sump and Sewage Pump Manufacturers Association members. And if you have a question, just ask. They're ready to help.